Welcome back. In the previous videos, as part of this week's lectures, we looked at the topic of machine learning at large scale. We started off by looking at what did machine learning at large scale, but done on a single machine, look like. And there are options available for doing that, for basically solving the problem in a single machine. But there are obviously problem statements for which even a single machine is not sufficient. That's when you need a cluster. What kind of algorithms are suitable for that? Then we went into the discussion on how does Spark help to make this process much smoother. Smart machine learning libraries, specifically MLlib. We discussed that. We discussed some nuances around best practices around usage of MLlib. So that's where we stopped with the previous video. In this video, we start to look at one of the more advanced concepts, which is called as MLOps, but it's actually becoming mainstream now. The reason it's becoming mainstream now is almost every institution has some application of machine learning in production, and therefore they are facing this problem and have to solve for it. So what is the problem statement? When you have models which are operating in production over a long period of time, what ends up happening is, firstly, you end up changing those models because you keep refining them, you keep changing the parameters, etc. Secondly, the data itself changes. So you have to keep retraining models on fresher and fresher data because the data is actually a reflection of your business, and the business has changed or the climate has changed. And third, the algorithms themselves are becoming more sophisticated. So as a result, the model changes, but also the feature engineering pipelines change. And lastly, and definitely not the least of the factors, is that the people change, right? The people in the commercial establishment changes, and the moment that change happens, newer set of data scientists, newer engineers come in, they change models, they make their own choices of how something needs to be solved for. So long story short, a lot of change happens, and when this kind of a change needs to be managed, and if you start doing this change management in an Excel sheet or in a notebook or a file, physical notebook, not Jupyter notebook, then you start to lose track of what actually happened in production. So the most famous example of this was something that happened in a bank. There was an ML model that was used as part of credit decisioning, and as part of credit decisioning, there is one of the critical input factors is is a person eligible to get credit? So there is a risk assessment that happens. In many cases, the risk assessment is actually being done using machine learning, and then the decision is taken whether to give that person a credit card or whatever credit product that they might be interested in. So as with all such banking products, regulation plays a critical role, and the regulatory requirement is that any single such customer-facing decision that is made by a bank or a lending institution needs to be traceable and explainable, right? So which means you need to be able to say, why did the decision get made? And secondly, what was the sequence of activities as a consequence of which that particular decision was made. So the sequence of activities means what model, what data, what parameters, when was it invoked, what time did the answer come back, when did the customer get informed about it, etc., etc. So what happened in this bank was that there were a lot of models, and the models were changing quite frequently, like we spoke about. So as a result, at one point in time, the model that was running in production, which was responsible for this credit decisioning, was something that stopped being as effective as earlier when it was first rolled into production. But the people who wrote the models were no longer there in the company, right? So as a result, nobody could actually go and change the model or take a look at what was happening behind the scenes, and nobody was even sure, right, which version of the code was actually promoted to production, and therefore which version of the model was actually running in production. So at some point, the regulator caught on to it. There is no traceability, right? There is no specific code that actually produced that model that anybody was authoritatively able to prove, and that resulted in a hefty penalty. So these things are very, very taken seriously in many verticals or domains like financial institutions or insurance, etc. So definitely something to keep in mind. Why did the term MLOps come into play? I think it's more a play on the word, rather the phrase DevOps. DevOps is the more classical and popular cousin, right? It originated from the time of effectively software engineering agile practices. DevOps refers to the fact that when software gets produced, basically when development happens, there's a lot of operational overheads that need to be managed in order for that development to see the light of the day. Meaning, in order for the development to actually become deployed in production and create the impact that it was supposed to create. And as a result, if nobody really understood how that was happening, how the code was being promoted to production, then you get this situation where potentially unowned code becomes responsible for driving business, and that's very risky. So DevOps became this practice of a set of practices around how code needs to be built, how does it need to be tested and deployed, and so that became a practice of its own. A lot of operational best practices have come in as a result, tooling as well. So MLOps is something similar, because at the end of the day, the code that produces ML algorithms are effectively similar to the software code that goes into applications, but there are some key differences, right? So let's take a look at that in this particular video. First and foremost, what is MLOps? Let's formally define this. It's the set of operational processes which manage ML models, their code, and the data that they rely on. So unlike software, which is basically just purely code, here there are two other unique elements that come into play for MLOps. One is the model itself, and of course the code, right? And then the data. So how does this come about? First and foremost, the code that denotes the model is basically the algorithm along with the feature engineering pipelines, the data pipelines, etc. All of that put together is the code. That code has to run on data in the first place. There is input data, right? That's associated with it. That input data could be voluminous or not, that doesn't matter. But the fact is that data has a characteristic. That data has a schema. The data has a certain distribution. So one example here would be if you use a machine learning algorithm for classifying, and let's say you picked on a couple of different approaches possible. So one of the algorithms could be a neural network classifier. Another one could be a naive Bayes classifier, a Bayesian classifier. The data on which the classifier is trained on has to have certain prerequisites in order for those algorithms to make sense. So specifically for naive Bayes classifier, the data has to be identically and has to be identically and independently distributed, which means that the data cannot be having correlations between each other. So you might start your analysis by verifying that the correlation between variables, the independent variables, is not there. But then over a period of time, as your business changes, as the new set of data gets collected, these correlations might start coming in the data set. So at that time, because the data has changed, right, the code that you have written might still be syntactically correct, but the model that you're running in production, which is the model that you've trained on this correlated data, may no longer make sense, right? So that's why it's important to track the data along with the code when you start to think about what version of the model is in production, what was it trained on, etc. So we spoke about the code, we spoke about the data on which the model runs, basically the feature engineering pipelines, the model prerequisites, the assumptions behind the algorithm. All of those are constraints that you put on the data, and of course the model itself, right? So what I mean by model itself is, at the end of the day, the code produces an artifact, right? The code is basically a set of, like I said, feature engineering pipelines resulting in model getting trained. Once the model is trained, the model is manifested as a pickle file or a jar or one of these common ways in which models get packaged. And then once it's packaged in a certain way, that artifact is what actually gets shipped to production for execution. That's what I mean by model here. The reason I'm making this distinction again is running code over and over again might or might not be practical. Let's take an example of deep learning. We'll take a look at that in the next week's lectures. The code might actually be a very, very complex piece of code, right? Or the code might be simple, but the data volumes are so high. The number of parameters could be in the billions, like is the case with GPT-like algorithms. And you can't just keep running the code again and again every time you want to do something, right? Every time you want to use a prediction from that particular model, because the cost of running the code at that large a scale is actually quite high. You don't need to keep training it, basically, right? You can use trained models and deploy them in multiple places and move on. So therefore the models themselves have to be tracked. So set of operational processes to manage ML models, their code and the data that they rely on. That's what MLOps is concerned itself with. What are the key steps involved in this? First and foremost, the model, when it runs in production, is presumably doing a scoring activity, like or classifying or whatever, right? That model run is very important that you track that, right? You need to know when was a run done, what data was it run on, which parameters were set, right, beyond the defaults, and then the result that came from it. The result could be as simple as just the score value, or the could be an evaluation metric. We spoke about evaluation matrices briefly at the end of the last video, or could be the data distributions, the value of the parameters, etc. So tracking the model run is a key step that's involved in MLOps. Second thing is because it wants to constrain the way in which models get deployed in production, because you want to have control on that. The packaging of the code in order to create the models in the first place in various environments, that is also part of MLOps. What does various environments mean? And we'll take a look at some examples in a couple of slides. It means that you're not going to be doing everything that you want to do for machine learning in production, right? In production environment directly. You will first start off in development environment, which means you do some development on the code, presumably in your Jupyter notebook or in your local IDE on your laptop. You test it out at small scale to make sure that it's doing the right thing. And then once it's ready, you put it into some kind of a cluster or an environment which trains on bigger data set and potentially a replica of the actual data set, or as close to a replica as possible. That environment is what we call as staging, right? And in staging, you actually do the effectiveness runs, the evaluation matrices, right? All of those good things. And it's in staging also that you spend time comparing it with other models, potentially doing model tuning and parameter tuning, hyperparameter tuning, etc. All of that happens there. And once that's done in staging and you've got the final model, that's the final model that you then ship to production, right? So because you have to deal with multiple environments and the code itself moves to the staging and then finally the model gets moved to the production, packaging the code becomes like an important consideration. Because at the end of the day, almost any ML algorithm that you use today is not just a standalone code. It's actually critically dependent on some libraries, right? Either the algorithms themselves are part of some libraries like Spark MLlib or Pandas or NumPy, or you borrow it from open source, like from third-party contributors. So, and the other consideration, the other problem that we find here is that oftentimes the software versions change. What used to work in Python 2.x doesn't work in 3 anymore because the API standards have changed, etc., etc. So what is very important to package here is not just the code, but also the artifacts, the dependencies, all of that which go around it to make that code working, right? So that's also part of the packaging. The third step that's part of MLOps is the management of the model artifacts. So here, what do the model artifacts comprise of? Obviously, it comprises of the actual model itself, but the model might have seen many changes. Therefore, you want to look at versioning every single change, right? Attaching just a different version, different nomenclature, even if it's the same nomenclature, just a different version, and use that as a basis for tracking what's happening. So versioning is an important consideration in terms of model artifacts. Documentation, super important. Almost always we struggle with this, or we'll tend to think of it post facto. But MLOps as a practice makes you think of it upfront, right? Makes you think of it as part of the model deployment process. And then finally, when you think about deployment itself, you could actually have deployment into multiple different ways, right? One is a scoring model deployed as a scoring API. So the model is deployed as a container or as an API, and then whenever somebody needs a prediction from it or a score from it, it goes rather somebody makes a request through REST and then gets the answer. Right? In that case, the serving interface for that model is actually an API. In another case, the model itself could be deployed as containers, and the containers themselves are code that gets linked to the main code that are also running in containers. And then the serving interface becomes basically what's called as an RPC, or a remote procedure call. Basically, it's one process calling into another process as part of the same machine, right? So in that case, the RPC is the serving interface. So bunch of different types in which possible. Pickle, of course, is a very common thing, right? So you package the pickle file as part of your scoring code, and then it gets invoked as part of that pipeline. So deployment to these serving interfaces is a critical step. So imagine if you had a model that was deployed to an API. The API is running actually at a remote endpoint. How do you control for that? The API might have its own versions, and then the API request bodies could change because you've changed something there. All of that is actually part and parcel of the deployment to the serving interface. Okay, so now let's look at some of the problem statements that MLOps tries to address. So what are the most common problem statements that you'll see once you start doing things in large scale is which code change that you made, what parameters were used, and what data inputs went into a particular result being computed. So this is that bank example that we spoke about, right? Why did that end customer get declined for a brand new credit card? That was the result. The decline was a result, and we need to go back and look at what resulted in that particular result, which means we need to go look at the data that was provided by the customer, which is available, right? Most banks have data governance systems, so the data is available. The parameters for the model are also potentially available because it's running in production and the parameters don't change that often. But what code change of the model produced that particular model file which ran in production? Nobody knows, right? That was the problem. So here, to trace a particular result back to these three parameters with these three factors is an important step. Now, running things in a Jupyter notebook, the ease with which you work with notebooks is phenomenal, right? So in fact, I would say the advent of a notebook interface became one of the key reasons why the job title of a data scientist became so popular, because a data scientist who typically comes from a non-computer science background, right, could end up actually doing development of new models without having to understand the engineering chops, right? Which means they don't have to understand how this code packaged, how is bunch of different compilations happen, what role does the environment play in actually ensuring that the compilation is successful and the run is successful, how to troubleshoot and debug errors, etc. Bunch of different things that software engineers take for granted or have learned as part of their career. A data scientist typically does not get a chance to learn that. And then for that data scientist to contribute, the notebook interface, which gives instantaneous feedback, which allows you to run without having to package things separately, without having to deploy things separately. All of that is very, very powerful. But the flip side to that is you don't actually have traceability, right? You don't really know what combination of steps resulted in a particular output that you see in the notebook. So let's say you go through a multi-step notebook, and each step you ran some, checks to ensure that the output that's getting produced is what you expect. So bunch of feature engineering steps, you look at the features that get engineered, everything looks legit to you, you move on, then you start looking at the parameters that feed up into the model, you check that and that looks fine, and then the model itself executes, and then you find that the F1 score is not good, right? The evaluation metric F1 score is not good. So then you go back and change parameters, and then you run it again, the F1 score is still not good. Then you change a bunch of parameters, like you do it like 10-15 times, and then you find out that maybe the feature itself is wrong. So you go back and do correlations, as one of the steps that you missed out earlier. Then you removed some features, and now you do this entire thing again. Bunch of 10 parameters that you changed, and then finally the notebook usage is over because you've arrived at a model which you think is the best. But if you then said, okay, look, this seems like the answer here is not as optimal as what I got like 10 runs ago. What does 10 runs ago mean, right? In the context of a notebook, what happened 10 runs ago? Was it just a case of running that particular cell in the notebook again and again? Or did you change some of the things and you had to trace it back to that, right? So all of those became, things that you had to, really care about when you started to, have multiple different versions of the code that existed, because the notebook, way of coding allowed you to actually do changes on the fly and not have to worry about it. So that's one of the first problem statements that you start tracking, that you start solving for with MLOps. The second motivation here is that the dependencies on libraries that you need for the models to execute, those dependencies are notorious, right? And anybody who's done data science and hands-on will know it. You need to have all of the different versions of the code, like I said, the Python 2.x versus 3.0. That was a big change when it happened last year. Actually, was it 2 years ago? Whatever, yeah. So it happened recently, but that was a very big change, and especially for ML algorithms. So when that happens, it becomes hard to reason about, why did something fail in production? Because the environment is completely different, right? Even though it's Linux, even though it's Python, even though it's Spark, despite all that, there's a bunch of other dependencies like software versions, third-party software, etc., which are not being packaged correctly. This is one side of the story, right? The other part of it is you might actually end up coding some pretty wrong things into the code without knowing that these are not best practices. So things like having version controls for every single part of the change that you do, which means that you make a change, then you check it into a code versioning system like Git, right? That allows you to keep track of every single change without having to worry about what change happened at that time, which resulted in that particular result. So those all become problem statements that you have to deal with. Then the way in which you package a model turns out to be quite a challenge, right? In some cases, we've seen people ship code, right, directly, not the model, because the code can be compiled in a different environment along with its dependencies, so that the model gets generated afresh. That could work if the training is not a function, right, of the environment, or the training can be made better because you have access to better data, like is the case with like staging and UAT environments, which allow you to have a replica of the production data typically. But yes, it's important to understand that what you ship from one environment to another may not be actually producing the same model. Therefore, some people prefer Uber jars. Uber jars are basically one jar to rule them all, right? One jar to bring all the different other jars and package it together. And that's fine. That works great. But imagine if you have to start shipping around Uber jars all the time. These run into like hundreds of megabytes. And firstly, you can't send it by email, obviously. But even sending it by SFTP results in, somebody just waiting for some time before the transfer is over. And then somebody needs to keep track of it. Version control systems with Uber jars become very, very sizable quickly, right? Because every time you make a change, you're actually versioning, an Uber jar which is like 500 megabytes as an example. So yeah, so these things you have to pay attention to, and that's something MLOps helps you with. And then finally, evolving the models that's going into production, and understanding why did a model evolve, right? What changed? How did it change, and tracking all those changes? That's a challenge. MLOps helps you with that crucially. So one of the most popular tools for MLOps is a open source project called as MLflow, and that's something that ends up getting used all the time by many different software vendors. So I'll encourage you to take a look at it. We will spend some time on it in the next video. Thanks.